So this talk's a little bit different in that it is a little bit more abstract. It's not a speeds and feeds talk, it's more about concepts and architecture. The other thing I should note is this talk is delivered in a little bit of a different way depending upon who's giving it. I guess the brainchild of the whole concept, the MeDiCI concept, is in the corner of the room somewhere. Professor David Abramson in the corner of the room. We both have a part in this. I suppose I'm one of the individuals that helps to create the platforms. So, on with the show. So it's a bit of a story of data locality, performance, namespace, and financial complexity. I will dig into that, okay? There's a little bit to that, right? So we need to zoom up a level at the campus scale. And a few people have seen this build before, but these are very large, what they call super science institutes, not dissimilar to large scientific research organisations in the United States. We focus on a lot of life sciences, a lot of translational research is starting to occur. They're all big in terms of imaging. Hundreds of terabytes a day of data come out of these places. There's an eclectic mixture of data. We have everything from simple engineering physics through to nanotech, Iron Man style stuff. So we have this disaggregated kind of set of supercomputing resources as well. I guess I could put it best by saying that every man, woman and child seems to build a supercomputer in some way. A little supercomputer, that is, and they put them in their buildings. So compute and storage are connected tightly together in these places, and that's something that's kind of happened in history. It's a little bit of a legacy thing in some ways. That's got its own problems, and these little supercomputers were not always large enough to containerize all of our big workloads. So there's an answer and a win and a way to that, though, and we'll get to that. So, of course, I said financial complexity. All of that leads to an interesting issue in terms of consolidation. The almighty dollar, as you say, causes some interesting pain points. And I guess as a consequence, we have to think of better, more efficient ways of doing things together. Problem is, when you have these gigantic buckets and silos of data, you need to surface them somehow. So we've ended up in some interesting circumstances where instrument outputs and scientific endeavours grow, but budgets for storage and compute do not. That's our own sort of scenario. It's half true, it's mostly true. In the United States, I know there are similar circumstances where scientific instruments get thrown into big organisations and everybody's left scratching their heads thinking how they're going to containerise these problems. The square kilometre array in our country and other countries is a good example of that one. How are you going to deal with that? So we recently got a new machine called a lattice light sheet microscope. It's spitting out a lot of data, genome sequences all over the place, single molecule imaging, super resolution microscopy, you name it, we've probably got it. To add another complexity, the university and the powers that be said, you know what, we don't really want your research intensive infrastructure to live on campus. We want it to be in a data centre 30 kilometres away. That's got its own problems, latency, co-locality, getting to the actual infrastructure is hard, possibly bandwidth. It all got a little bit difficult. So at some point in time, David sat down and he said to me, we need a way to actually deal with this and fake that concept of near locality of data. It's caches, man, caches all the way down. And it's a concept of, in computer science, caches kind of do this magic thing where they abstract everything. It's been the same forever. So we needed a way to satisfy parallel I/O requirements. We had to have a way to make an eventually consistent model. It had to be distributed. We had to have a single namespace. It had to support object and POSIX possibly. Maybe that was a nice give me at the end, I'm not sure. It had to be horizontally scalable. So what became of this MeDiCI thing, right? So David said, find a way, and I said, gulp. So the problem definition was, how do we provide parallel access to scientific data through a multitude of protocols and give the illusion that the data is next to the applications on a budget, keeping the right data near the right type of computational infrastructure, noting our budgetary constraints, right? How do you do all that? Right? So that's kind of the magic behind it. So this isn't my diagram, this one's actually David's, and it kind of gives a very brief overview of sort of the way this stuff gets tied together. And we basically have our instruments. We have our local cache. In our case, it's GS7Ks. We use GS7Ks as building blocks at the moment. But it's commodity infrastructure. We could technically build this with anything, right? And then we go out to a disk cache over what could be a really fast network, could be a really slow network, out to long-term storage, which we've glued to the back of it in the form of tape. We love tape, right? We still love tape. Anybody that says it's dead, I think we could have an interesting offline discussion when we're at this scale, right? So yeah, I'm happy to debate it, happy. So what are we doing? We're using Spectrum Scale's AFM in the grid scalers. At the time, I don't think there was anybody else trying to use AFM in grid scalers. Just out of a show of hands, is there anybody using AFM out of grid scalers? Cool, okay. There's a couple of people now. All right, you may have been doing it before us, I don't know. But yeah, we were pretty kind of new to it, and it was very, very new when we touched AFM, and there's some interesting problems in that. So cache and home. Anybody that knows about AFM knows it has a cache and home relationship. You dump data into the cache and it ends up at home using a parallel I/O mechanism, using the NSD protocol. You can flatten pipes with this stuff. In another version of this talk that we give, you'll actually see our ability to saturate pretty much any network pipe, which is kind of cool, right? Kind of a headache for the network guys too. So I say keep calm because nothing is perfect. I don't like to give talks where everything just sounds wonderful and breezy because nothing is perfect. So we've had some interesting kind of road bumps along the way, or speed bumps along the way, and I'll get into that. So turns out that doing parallel I/O and parallel access, the same namespace in different places where the namespaces and the name maps don't exist in the same places because your campus doesn't use the same namespace and someone uses this version of Active Directory there and someone uses this version of Active Directory there is hard, right? GPFS natively had some commands to deal with that in mapping called mmName to UID and mmUID to name. That's great because it meant we could make effectively what we kept referring to as a big hash table. I will convert your name here to your name there on the other side of the file systems at home and everything will be great, right? Wrong. So as it turns out, the code was missing from Spectrum Scale. So not only was it missing, the structs and classes didn't actually exist to even facilitate it. How did we know that? Well, one day we picked up the phone to DDN and said, we think we found an interesting problem. And DDN said, oh, that's quite interesting. Let's get a case logged. And through some contacts and good collaborations that David and I have fostered over time with IBM, we got one of the head AFM engineers, a guy named Venkat, on the line. And Venkat said, yeah, that doesn't exist. How did you come up with that? We went, oh, okay, well, can you fix that? So we started a long collaboration process that took a couple of months to engineer the ability for AFM to transparently map UIDs between completely separate entities in home and cache, despite having the same consistent namespace. And it works. And as it turns out, we were the first ones to do it. You will see this in GPFS version 5. So it's pretty cool. Network stumbles. So we had at best 10 gig around the campus, okay? 10 gig out to the data center. When you're dealing with data of this size and storms of this nature, that's not actually that great, especially when you're bouncing through 1,000,001 firewalls. We had a lot of fun dealing with this stuff, firewalls, DMZs, MTUs and whatnot. So we had to spawn a little mini project to allow us to actually do this stuff properly across a campus scale. We needed to get to 40 gig and 100 gig on a ring of nodes. We successfully did that. It took quite a few months and a lot of work, a lot of collaboration with our network engineering people, and we got there. So we didn't flatten the network. Every time we wanted to transfer data, everybody else would panic. Well, we actually got a few phone calls to that effect. It's like, what are you guys doing? Stop it. So we had to separate that kind of concept. And we did that successfully. So recovery storms. AFM, I will say, is a work in progress. I think people agree in general. People who clearly have a lot of experience agree. It's much better than it was, but we still have recovery storm issues. If you were at the Spectrum Scale User Group meeting the other day, they talked a little bit about this and how much work's being put into it. But when you're trying to recover tens of millions of files, AFM doesn't always quite keep up. IBM's working on it for us, and there's several customers globally who are putting in efforts with that as well. Scaling to 100 millions of files in a single file system is required for us. There's people using billions, so that there are billion scale customers. We know about them. We know they're out there. We're little compared to that. So we had this assumption of what users would do. This is a bit of fun. We thought users would put things in the cache at the remote site from the instruments, and then they'd process out at the supercomputer out at the remote data center. That plays pretty well. People have been doing that. It's been working really, really well. People confound us all the time and make us look silly. We think we know what people want. We kind of get it right. And then this happens. They start running the supercompute jobs locally and remotely at the same time, triggering staged events between places with their workflows. So we've ended up with a circumstance where we've got the same data namespace, ended up everywhere. That much was intentional, but the users leveraged it in that they started to run on every supercomputer we own with their own workflows because they're smart enough to write them that way to trigger and trigger and trigger across the namespaces in the AFM caches. These guys are pretty clever. So we didn't really expect that, but what does it mean? It means huge utilisation for the whole campus. It means the resources can be used as best they can, right? So big tick, I suppose, in that regard, unintentional in some respects. A bit further on, we did some work about a year ago between us, UCSD, SDSC, ARNet, Chris in the audience, he helped us a lot with this as well. So Chris Myers. So we actually managed to span this AFM concept across the globe, all the way to UCSD. We actually managed to further get a full 10 gig line rate across to UCSD using the AFM transport over the NSD protocol, NFS protocol, using a lot of tuning with latency effectors removed. Further on, using the Pragma network, we're pushing into Asia. We've done some initial work there as well. And we're actually finding that this could be a really good use case and model globally for data movement and combined workflows. So this is all working quite well. It's working quite nicely. We're getting acknowledged for it, which is really nice. David's collected a few different bits and pieces of awards now for this. One actually a federal government one quite recently, the ACS Digital Disruptors Award. Things are turning out really quite cheery for this, and we think we're really onto a concept that works well for data movement globally. Yes, it's different than Aspera. It looks different than traditional DTN kind of networks. But the way I look at it is that we're putting the hands and the power to the users. It's autonomous. You don't need to worry about where your data's sitting. The concept of caches all the way down is very nice. It means that the data could be cold in tape. It could be sitting in the back end of the DDN disk somewhere at home in a GS12K, or it could be connected all the way down in that tape. It doesn't matter. It keeps things cheap and deep, and it keeps things where they need to be when you want them. With that, I'll put some thank yous up. I want to thank David for his mentorship and sense of adventure, which is required and requisite for things like this. QSIF, who are part of the organisation we work for, my colleagues at all the other research institutes who I'm constantly pushing around and kicking and punching to get them to help me to make this all work. A couple of the industry associations which we've been awarded with certain awards, and Justin, our DDN representative locally at DDN, for his support and his camaraderie. And with that, yeah, I'll open it up to questions. Thank you.
Thank you, Jake. All right, any questions? An arm up over here.
You alluded at the end that you were also hiring.
Oh, that's a great question. So you may have made, or some people may have made an assumption that we were using TSM or something to that effect. Maybe you didn't. We're actually using DMF in this particular case because DMF existed. DMF was there, and we made a conscious choice not to throw everything up in the air and say, well, we should throw a whole new IBM backend into it. It didn't make a lot of financial sense. How we're doing it is actually an NFS interconnect out of the back of the home, and we're effectively chaining the cache, or chaining the home to a DMF NFS export into the tape layer, into a DMF cache. IBM will tell you that that is not a supported principle. It works. Okay. If we ever broke it, and we haven't broken that aspect of it before, we would have to have a conversation. There are discussions happening in the back end with HPE SGI about native support for GPFS now. What that means yet, I don't know. Okay. Good question, though.
One other question. Anyone else with a burning question here? Yeah.
Oh, that's Japan. It's actually Japan. Sorry. AIST. It's actually Japan. Yeah. No, there is nothing currently in North Korea or South Korea. No. No. I promise. I think I should get off the stage now.
All right, thank you, Jake.
Thank you so much.